Okay, in the last video, we talked about the probability of AND case compound events, and we said that in this video, 5b, we're going to talk about the special case for that, which is called independent events. So just to review what we covered in the last video, we found that the probability of an event A and B occurring, both occurring together, would be the probability of A occurring times the probability that B occurs given that A has occurred. A conditional probability, and that's the catch, that the second probability has to be a conditional probability. Or we could have listed the probability of B first, and then it would be times the probability that A happens given that B happened. Those are the true AND formulas that work in all cases. And in the OR case, we found that there was a special case, which was if events were not overlapping, then there was nothing to subtract off, and that ended up simplifying the OR formula. So you can go back to Lesson 4 to look at that if you're interested. But there is also a special case for the AND situation we're considering right now, and that's if the events are independent. So let's define events independent this way. An event is considered independent if the probability of one event does not depend on the probability of any other event happening. Or you could think of it as if one event happens, it doesn't change the probability of the other event happening. So the data that we've been using in the lesson 5a, actually we're going to analyze further, turns out to show that the events girl and reading a book are not independent of each other. To see why, let's consider what you would say if I asked you this question. What's the probability that a student likes to play video games? So there's actually three probabilities you could find to try to answer this question, all probabilities of people playing video games. Right? You could find the probability of all students who like to play video games. That's a simple probability, just the probability of games. So out of the 100 students, 32 of them like video games. That probability would be 32 out of 100, or 32%. Or you could say, well, let's find the probability of a girl liking to play video games. So that would be a conditional probability. The probability that someone likes to play games given that they're a girl. So out of the 60 girls, 12 of them like to play video games. So that would be 12 out of 60, which would be 20%. And then you could also have found the probability of a boy liking to play video games. So that would be the conditional probability liking to play video games given that you're a boy. So the boy determines the bottom of the fraction here. Out of the 40 boys, 20 of those boys like to play video games. So 20 out of 40, or 50%. So your answer to the question, what is the probability that a student likes to play video games, should be, well, that depends. Are we talking about all students, or are we talking about boys, or are we talking about girls? Because those probabilities are all different. That means that activity and gender are not independent. If there was no change in the probabilities, then we wouldn't have to say it depends, and we could say it's independent, which means not dependent. But because it does seem to depend on the gender, we have to say, well, it depends, and therefore we conclude that activity and gender are not independent. Okay, so how could we determine if two events are independent? One way is to just check any two of the three probabilities of one of the events, like we just did. So let's say I wanted to find out if gender and if entertainment choice are independent. So I could pick one of the values, say games, probability of games, and figure out what's the probability of games, the simple probability, what's the probability of games given that you're a girl, and figure out the probability of games given that you're a boy. And I could pick any two of those to find out, to compute. And if they do not match, then that means the events are not independent, like they were in this case. Sometimes we're not presented necessarily with the actual data where we could compute those things, but we might have some visual summary of the data. Like, for example, a segmented bar graph like this, some sort of a bar or side-by-side bar charts like this, where we have a percentage of girls who like to play games. This was 20%, so maybe we have a vertical bar here where 20% of it is shaded. And then for the boy, 50% of the boys like to play video games, so that would be 50%. So if we were just looking at visual graphs here, what would tell me that these events are not independent is the fact that the graph's percentages don't match. So if they visually look like they're not approximately equal, then we would have to say the events are not independent. Okay. Sometimes we have a tree diagram. Let's say we had a tree diagram where we talked about probability of in this group of being a girl and being a boy, and then the probability of liking a book given that you're a girl, games that you're given a girl that you're a girl, or Netflix given you're a girl, and the same for boys. So you could pick one of these end nodes, like games, and compare the conditional probabilities. If the probability here is 20% and the probability here is 50%, that means that probability is changing dependent upon what choice is made earlier in the tree, right? And that means that games are dependent upon gender because we have a different probability dependent on which gender I choose, right? So whenever you see probabilities that are varying across the different choices in the second column here of a tree, that's another way to indicate that we have events that are not independent. Okay, so what would it look like actually if gender and activity were independent? So I'm going to change the data in the table here. Of course, the counts would have to be different. So I've adjusted the counts here, different sample of 100 students. This time the data is going to show that these two things are independent. Now notice that if I just look at the counts, right, like of video games, let's say I'm looking at video games again, the counts for girls liking video games is 30 and the counts for boys liking video games is 20. It doesn't actually matter that those counts are different. The fact that the counts are different doesn't tell me whether or not something's independent. We're going to have to actually figure out what percentage of the girls and what percentage or proportion of the girls and boys like video games to compare that, right? We can't tell by comparing the counts. We have to compare percentages. It's the percentages that would now be the same. So if I were to find, for example, probability of anyone liking to play games, that would be 50 out of 100, 50%. Right? The probability that of the 60 girls, 30 of them like to play games, that would also be 50%. And of the 40 boys, 20 of them like to play games, that would also be 50%. So those probabilities would all be the same. So if I picked any two of them and they turned out to be the same, then that means I know that they are independent. These events, gender and activity, are independent, or these variables are independent. And if I had bar charts like this, these shaded regions of percentages that like games would be the same across both the genders, or at least approximately the same. Okay, if you had a tree diagram, it would look something like this. A probability of playing games would be 50% everywhere in the tree, and it wouldn't change depending on if we had a girl or a boy. Okay, so this special case, that when we talked about the OR formula, we ended up having to, the catch was that we had to subtract off the overlap, and disjoint events was a special case because it meant there was no overlap and therefore we didn't have to subtract anything. It gave us a simpler version of the formula. So similarly to the AND formula, independent events are the special case for the AND formula, and they're going to modify that formula. So just to remember what that means, so the special case we're going to say is if the probability of an event does not change regardless of whether or not another event happens, then the events are independent events, which means that the probability of B, for example, would be the same as the probability of B given A happening, and that would be the same as probability of B given that A does not happen. All of those three probabilities would be the same because the probability of B would just be the same in all cases. Well, if that's true, the AND formula, which we know in all cases, is this. The probability of A and B is the probability of A times the probability of B given A. This conditional probability can simplify. If we know that the probability of B is never changing because the events are simple, or the events are independent, then that means that this probability of B given A can simplify to just be the probability of B, the simple probability of B. And we get a slightly simpler version of the AND formula. The probability of A and B is just the probability of A times the probability of B, and we no longer have to have a conditional probability for the second probability. Okay, and just like we talked about, the fact that the probability of overlap would be 0 indicates that we have a disjoint event. We can also define a test for independent events, right? Two events are considered independent if any two of these three, actually if all three of these things are equal. So you can check any two of these, and if they're not equal, then that means the events are not independent. That's by far, I think, the best and most conceptual way to test if events are independent. Pick one of the events, find the probability of that event occurring for the entire sample space, and then find the probability of that event occurring given that the other event occurred, and see if they match. If they don't match, then that means that the event is not independent. Okay. Note, some books, actually a lot of books, use the simplified version of the AND formula, and they call that the test for independence. So they say, well, because if A and B are independent, it means that the AND formula simplifies to this. They say you can use the simplified version of the AND formula as the test. If that formula is true, then it means A and B must be independent. And it's true, you can do that. But the truth is, actually, that's more of a consequence of independence. It's not really the reason the events are independent. But I will mention it because so many high school math books do mention that as a test for independence. Okay, to summarize, for AND situations, the probability of AND case is the probability of A and B is the probability of A times the probability of B given A, or it can be the probability of B times the probability of A given B. And honestly, this is the most important part. You should picture a part of a tree and use that to help you remember the formula. If you want the probability of A and B, pick one of them to list first, like A then B. This is a simple probability, this is a conditional probability, and you have to multiply this one times this one in order to get the AND. And what this is saying is that you could list the A first and get this version, or you could list B first and get this version. So the reason why I wanted to show you in the last video the tree is that really is a helpful way to be able to reconstruct this complicated looking formula. Okay, a special case occurs if we have events that are independent. The definition is if the probability of B is unchanging, whether for the entire sample set, or whether A occurs or whether A doesn't occur. If B is constant, if that probability is the same, then that means the probability of B is independent of A, and A and B are independent. And that means that the general AND formula simplifies to this, where the last probability is no longer a conditional probability. We can also define a test for independent events, which really should be to check 2 of the 3. But we should mention that some books use the simplified version of the AND formula as the test for independence. Okay, that should be it for AND cases and the special case of independent events. If you want to go to the examples video, we'll work out a number of problems that use those ideas.